Today, the gradient and the directional derivative, these are very important in science. They have very important implications in all sorts of physics that go on and so forth. And the gradient has a very simple definition. The gradient of a function of two variables, and we'll do this completely analogous thing for more variables, is just the vector of partial derivatives. It's nothing more than that. So if I put df dx in the x component, df dy in the second component, that's the gradient of f. Very easy. So the gradient of a function is a vector valued function. And for instance, f of xy equals x squared plus 2xy. What's its gradient at a general point xy? It's this vector function here. We just take partial with respect to x. Let's see, it's 2x plus 2y, right? Oh, there it is. What's the partial derivative with respect to y of x squared plus 2xy? Well, it's 0 plus 2x. There it is. So it's just the vector of partial derivatives. The gradient is nothing more than that. But it's immensely useful, it turns out. Wait till you see the properties at the end. Consider z equals f of xy, and we move along a curve in the plane. So, and z equals f of xy, right, is a surface over some plane region that's the domain for that function. And suppose that as we have this surface, z equals f of xy, we also move along a curve in the xy plane, r of t equals x of t, y of t, a vector valued function. This is a vector parametric form for a curve that I'm moving along in the xy plane. So down here, this is my curve. This might be my map for the mountain. And z equals f of xy is my mountain. So I move along z equals f of xy mountain according to my trail map in the xy plane. And now my actual points where I'm moving on the mountain are x of t, y of t, f of x of t, y of t. This is moving along a curve, and I might ask, at what rate am I ascending or descending? What is my rate of ascension? I wonder how fast I'm moving up or down as I move along this mountain trail over the curve C on my map. So that's the question down at the bottom here. What is df dt? The derivative of f along the curve C is what we call this. If we want the derivative of f along the curve C, f being this surface here, well, never can make this quite the right side. That's df dt, right? F is the z coordinate, so I want the rate of change of z with respect to time is the rate at which I'm moving uphill or downhill, 10 feet per second or 2 miles per hour or whatever it is. That has to be the limit of f of the point at time t plus h minus the f at time t all over h, right? That's the derivative of a function of t. But f is a function of t through x and y. It's a function of a function. Chain rule. No wonder we did that last section, right? Well, if f is differentiable at x of t, y of t, then this is limit of right, by the linearization. For a differentiable function, f at x plus t plus h, y of t plus h is df dx delta x plus df dy delta y plus some e of xy in error between the actual function and this linear approximation. That was the definition of differentiable. It's equal to the linear approximation plus e of xy, where the ratio of exy to h, the distance you moved, h is the square root delta x squared plus delta y squared, is equal to 0. This is going to 0 as you get closer and closer to the point at which you want to take the rate. All right, well, what is this? This one, df dx delta x over h, has its limit. You break the limit of the sum into the sum of the limits, plus this limit, but this limit is 0 by differentiability, gives us df dx times limit h goes to 0 delta x over h, limit h goes to 0 delta y over h, but these are the derivatives, right? This is x of t plus h minus x of t all over h, and this is y of t plus h minus y of t over h. By definition, that's the ordinary derivative, and so we get the chain rule out of this. The rate of change of f along a curve is just the chain rule, the f dx dx dt plus the f dy dy dt. And that gives us this special case of the chain rule that we had before. And let's try it out. Suppose I move along this surface. F of xy equals 4 minus 2x minus y. We already know what kind of surface this is, right? It's z equals ax plus by plus c. It's automatically plane because it's a linear function, right? Ax plus by plus c. And so this is actually going to have, right? It's going to be a nice flat tilted surface. And if I move in one direction, I'll have constant rate of descent. So I'm not going to move in one direction. I'm going to let x of t equal t squared and y of t equal t cubed. I'm moving along this curve in the xy plane, which is the y equals x to the 3 halves, right? If you solve this for y as a function of x, you get y equals x to the 3 halves curve. Kind of like a parabola for shape. And here's your vector value parametric curve, right? R of t equals t squared t cubed for components. Now what is df dt? If f is this function of x and y, well, we can apply the chain rule and say it's df dx dx dt plus df dy dy dt. Evaluate it at the point we're interested in. Let's say we want to do this at time t equals 2. Well, at time t equals 2, we get x equals 2 squared is 4, y equals 2 cubed is 8. So we want to take df dx at the point 4, 8. That's the point, the coordinates on our map that we're looking at, 4, 8. Times dx dt at t equals 2, and then plus df dy at the point on our map, times dy dt at t equals 2. And what do I get? df dx is negative 2. df dy, you take the derivative of this, is minus 1. And dx dt, let's see, derivative of t squared is 2t, derivative of y squared, t cubed is 3t squared. So we just plug in all those derivatives of those points, and we get minus 2 times 4 plus minus 1 times 12. Minus 16, we're descending at 16 feet per second. Descending since it's negative, right? Oops. Now geometric, I'm sorry for the scribble, maybe I'll fix that if I get time before I put it up. Geometrically, this is what we were doing. The surface, we can plot it easily, right? If we just take x equals 0, y equals 0 in that equation for the surface, we get z equals 4, so we can plot 0, 0, 4. If we put y and z equals 0, we can plot, or x and z equals 0 into the equation. What was it, 4 minus 2x minus y or something like that, z equals that. We get the point 0, 4, 0. And if we put y and z equals 0, we get 2, 0, 0 in that equation. Finding 3 points on the surface, and knowing it's a plane means it's the plane that encloses this triangle as part of it, right? So it's this plane right here. If you want, you can draw a rectangle around it to enclose it. You don't have to do that. This is the plane that's the surface that we're interested in finding our rate of descent along it. Now this is our curve in the plane. Y equals x to the 3 halves. When you rewrite that, the 2 is off the end here. When you write that parametric curve y as a function of x. So we're moving along this kind of parabola-like shape in the xy plane, and coming down overhead, this, down like this, crossing right here, I guess, coming down, moving along the plane, what rate are we descending when we're at the point 4, 8, I should have put up here, along this curve. Yeah, 4, 8 minus 12 is down here. And when we're at this point along Mount Tilted Plane, at what rate are we descending? What is dz dt? Well, we just go back, and this is an application of the chain rule. df dt. Here's a nice way to write it. We said it's df dt, df dx dx dt plus df dy dy dt. If you think about that for a second, it's really the dot product of these two vectors, df dx df dy, dx dt dy dt, right? It's this times this plus this times this. But this is the gradient, and this is the tangent vector, right? dx dt dy dt is the vector that's tangent to any curve. when it exists. And so what the rate of change of f along a curve is really gradient of f dot r prime. So we can find the rate of change of this function as gradient of f dot r prime, or we can just use the chain rule directly, whichever one you like. But I thought I'd point out it has this nice interpretation in terms of gradient. It shows that the gradient really is an important quantity that comes into use here. You just dot the gradient with the tangent vector to wherever you're moving. Well, let's C be a level curve of f of x, y. Let's see. I was looking for this. Finish to the problem. Guess I didn't finish writing it out, did I? Let's see. Oh yeah, I did. I'm sorry. We found out it was minus 16 feet per second. Right, didn't we? So anyway, we already found the rate, and it shows us that when we're at this point, we're descending at that many feet per second or miles per hour or whatever it is. All right. And now we'll introduce this concept of a level curve. What is a level curve? Remember, it's a curve that intersects your surface with a horizontal plane. That's why it's a level curve. It's horizontal, a curve in the horizontal plane. That's the intersection plane with the surface. And so it's the solution, f of x, y equal k. Actually, that's the trace in the horizontal plane. When you project it down to the xy plane, then you call it a level curve. So it's the curve in the xy plane, f of x, y equals k. That's the projection of the trace, the intersection of the horizontal plane, projected down. All right. Now, along a level curve, right? You're not changing altitude. You're taking the intersection of the surface with a horizontal plane. So along a level curve, df dt equals 0. And the equation we had up there, that df dt is gradient of f dot r prime, becomes that equals 0 because along a level curve, df dt is 0. What does that show you? It shows you that along a level curve, because df dt equals 0, gradient of f dot r prime is 0, the gradient is perpendicular to the tangent vector. That means that the gradient is perpendicular to the level curve itself, right? The tangent vector is tangent to the curve, and this is perpendicular to that. So this is a very important property of the gradient, a geometric property. It is perpendicular to all the level curves, which means that if you draw a topographic map, that is a plot of the level curves. Here's maybe your topographic map of a mountain, right? Here's the one plateau, and here's another level path around the mountain. Here's a level path around the mountain. Here's another. You can see the topology of this thing. Maybe this is 40,000, whatever, little mountain. 40 feet, 20 feet, and 10 feet, the molehill, almost. Then the gradient of f has to be perpendicular to each of these level curves. Here's the tangent vector as tangent to any parameterization of the curve. And the gradient has to point perpendicular. But which way? Does it point this way or this way? In fact, it points in the direction of increasing function. So if these are the level curves getting higher and higher in altitude, 0, 20, 40, then it has to point this direction. So it's perpendicular to the level curve, pointing in the direction of increasing f. This is a very important concept in numerical analysis where you're trying to find the peak of a mountain or something, or the bottom of a valley. There's a method of steepest descent where you try and travel down the valley or up the mountain in the direction that's steepest, up or down. And you try and reach the peak as quickly as possible by going in the direction that's steepest. You use the gradient. So this is an important concept for optimization in general because of that. As well as being important in lots of things like electromagnetism. You'll find the gradient appearing for electric fields and so forth. All right, now we want to introduce, in terms of the gradient, an additional application. See how important it is? It tells you the direction perpendicular to level curves. It tells you also this, in the direction of steepest descent. The directional derivative it also helps you define what's called the directional derivative. We said we could take a mountain that has an equation, and we can find the slope of the tangent line in the x direction. Maybe here's x, I find the slope in that way coming down the mountain. Here's y, I can find the slope coming down that way. Why can't I take the slope in any direction, right? Of course I can, right? How do I do it? Here's how you define the directional derivative in the direction of a unit vector u with components e1, e2, or hk, or something like that. It's the limit as h goes to 0 of f of x plus th, y plus tk minus f of xy all over t. All right? This is moving you in the xy plane in the direction hk, right? This is a parametric curve for a ray coming from the point xy in the direction hk. So you're moving along a ray in the xy plane, taking an increment of f moving in that direction divided by t. If you take the limit as t goes to 0, this gives the slope of the tangent line in the direction hk. In fact, if you did a rotation of coordinates, this would default so that x was in the direction of hk. You'd find out that this actually is the partial derivative with respect to x in that turn plane. So this is just the definition of partial derivative turn in the xy plane to the direction hk. And now, if you notice, by putting in u equal 1, 0, this becomes x plus t, y, minus f of xy all over t. It becomes the partial derivative. So the special case of partial derivatives, when you take u equal 1, 0, you get the partial with respect to x. When you take u equals 0, 1, you get the partial with respect to y. And here's what we have for the picture. More generally, right, we take here's the surface here, z equals f of xy. We want to find the slope moving in this direction, the xy plane. hk equals u at xy. And so within the plane that contains that vector and is vertical, right, we want the slope of the tangent line. Effectively, we're taking the slope of the curve that's the trace in this tangent line. Well, it's just this definition. From what we just showed on the last page, duf, the slope of the tangent, right, this is a function of, if you think of this as a function along the path, you increment it with t like before, then it's gradient of f dot u is what this comes out to be. So limit as x goes to 0 of x of f of x plus th, y of th, minus f of xy all over t. If you write out the chain rule like we did before, you get gradient of f dot u, where u is the direction of your motion. And so, let's try that for this one. Suppose I wanted to find the directional derivative to the function z equals sine of x minus y. Well, it's kind of hard to draw probably. It oscillates up and down. You can actually draw this. But if you rotate the coordinate system, it's a lot easier. All right. Don't you just love this, how they interrupt you right in the middle of your big presentation? Find the slope of the tangent in the direction 1, 1 of this surface at the point pi over 3, pi over 6. You go to the point pi over 3, pi over 6 in the xy plane, and if you're moving out in the direction 1, 1, what is the slope coming down the surface overhead? You have to kind of think of that picture. I think it really helps. Well, you need to calculate the directional derivative in this direction. So remember what the theorem said. To calculate the directional derivative, you can take gradient of f dot u, where u is a unit vector in that direction. So first or second, I calculated u, the vector I wanted, 1, 1, divided by its length, square root of 1 squared plus 1 squared, right? Root some square root. Gives me the vector 1 over square root 2, 1 over square root 2 is a unit vector in the same direction. Then I calculate the gradient of f at the point. So I take the gradient, that's the vector of partial derivative. Derivative of sine x minus y is cosine x minus y. Partial derivative of cosine x minus y, sine x minus y, let's see. Yeah. Partial derivative of sine x minus y with respect to y is cosine x minus y times derivative minus y is minus 1. And so I get cosine x minus y minus cosine x minus y is the gradient. That's showing what I did. At the point pi over 3 pi over 6, we need to evaluate it. Cosine x minus y pi over 3 pi over 6 is cosine pi over 6 is 1 over is square root 3 over 2. Minus cosine is the same as minus square root 3 over 2, and we're going to dot product that with u. So gradient of f dot u at the point, it gives us this dot product, which comes out to be, well, these cancel, you get 0. Apparently we're moving, the direction u moves in a horizontal along a level curve, because we're not moving uphill or downhill. And then an interesting point, we just talked about that the directional derivative in the direction of the unit vector u, which is an arrow on it, is gradient of f dot u. So the directional derivative is actually a number, it's the slope, but it's the slope in this direction u. If it's this, then by the dot product, that's length of the gradient, length of u, cosine theta, but u is a unit vector, so it's length of the gradient, cosine theta. That tells you something very significant about the gradient. What is the direction that you can make the gradient as big as possible? Make it as big as possible by making cosine its maximum value, which is 1. So the largest directional derivative occurs when cosine theta equals 1, where theta is the angle between gradient and u. That means you want theta equals 0 to make cosine 1. That means that gradient points in the direction of u, or u points in the direction of the gradient. The biggest directional derivative occurs when you move u in the direction of the gradient. It tells you the gradient is the direction of steepest ascent, as I was just talking about a little bit ago. That's the proof of it. Oops. Did the wrong way. Oh, I know, it's on the next page. Hold on. I didn't get a chance to put these on the computer yet. So there's the conclusion we just said. When theta equals 0, that's the direction where you get the largest gradient. What's the value of the gradient? We showed that it was the absolute value of the gradient, or the length of the gradient. And so that's what we get. U equals the unit vector in the direction of the gradient, gives the direction of steepest increase, and its value is the gradient. And then what's about the direction of steepest decrease? Well, that's just the opposite direction. Then cosine is minus 1. When you go minus the gradient over its length, and then the value is minus the length of the gradient is the value of the directional derivative. So that's the maximum and minimum directional derivative. And moreover, it tells you something else. Any angle between, if you turn through an angle theta, the value of the direction of the derivative is just the maximum value, gradient of f, times the cosine of the angle you turn through. It tells you that actually the gradient is just turning in the tangent plane. And you get the steepest slope when the tangent plane is when you're in the direction of maximum tilt. And as you move around in the tangent plane, you just multiply that gradient by cosine theta. The opposite direction, when theta equals pi, gives you the direction of steepest descent going down the tangent plane. And all this extends to more dimensions. Now suppose I have w, a function of 3 variables, x, y, and z. Now the gradient of f turns out to be orthogonal to the level surfaces by the same kind of argument. A level surface being a constant equals f of 3 variables. And so it's the level surface that passes through the point x, y, z, the gradient is perpendicular to that at the point, and again it points in the direction of greatest increase of f. This is important like an electric field in 3 dimensions. You want to know what's the direction in which I move to make the electric field increase as rapidly as possible? Well, you take the gradient direction. And again, the directional derivative has the same formula, gradient of f dot u. It's just got three components now. The gradient has three components, df dx, df dy, df dz. It's a vector of three partial derivatives. And when you dot it with a vector in three dimensions, u1, u2, u3, this becomes the directional derivative in three dimensions. So we can do one more problem like that. Here it is. Find the unit vector in the direction of most rapid increase of f of x, y, z equals this polynomial function at the point 1, 1, minus 1 in three dimensions. And the rate of change in that direction. So what's the gradient? It's the vector of partial derivatives. I take partial with respect to x. I get 3x squared times z squared plus nothing, 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 because there's no x, right? I just get 3x squared z squared. Partial with respect to y, only this term has y, so it's 3y squared z. There it is. And partial with respect to z is here. And then I plug in the point at which I want to find the direction of most rapid increase. 1, 1, minus 1, and I get the vector minus 3, 0. You can pause your video to figure this out as you go. I'll do this faster than I would in class. And so now what's the direction of steepest increase? It's the gradient of f, minus 3, 0, divided by its length, which is the root sum squared of its components. Minus 3 squared plus minus 3 squared plus 0 squared. It's just minus 1 over square root 2 minus 1 over square root 2 is the direction you move to make this function increase as quickly as possible when you're at the point 1, 1, minus 1. And what's the rate at which you're increasing? Well, that's just the length of the gradient. It's root sum squared minus 3, it's square root of 18, or 3 square root 2. Well, that's it. Pretty neat applications, and we'll be using this again in upcoming sections.